The James Webb Space Telescope is one of the largest and most complex science programs that has ever been undertaken. It is designed to answer unique questions about our position in the universe. In this video, I will discuss 5 observations that Webb's telescope will make, which will change our understanding of almost everything. The first objective of the Webb telescope is to make observations of the early universe. This is a period when the first stars and galaxies started to form. To better understand what Webb telescope will be observing, let me quickly tell you the history of the universe. During the first picoseconds, the universe was born. Actually, Webb telescope is not going to observe this period. After this comes the early universe, which lasts around 370,000 years. Various kinds of subatomic particles were formed in this stage. The famous cosmic microwave background picture captures this period. Again, Webb telescope is not observing this. We have other satellites like the Planck telescope designed for this kind of observation. After this period, came the Dark Age, which lasted from 370,000 years until about 1 billion years. During the end of this period, large-scale structures like galaxies and stars started to form. They start to emit the first sources of light. I will discuss how these first lights were produced in future videos, but for now, let's take it as it is. The first stars and galaxies in the universe that were formed in these stages are the roots of everything we see today. It represents the initial conditions for the study of galaxy evolution. Because of this, understanding the first light from these first galaxies is extremely important. Currently, we have a huge gap in this understanding. Because of Planck satellite and CMB data, we know a lot about the very early universe. And because of Hubble and Spitzer telescopes, we know a lot about late-time galaxies. But we don't know much about these early galaxies. This is where James Webb Space Telescope with its infrared detection instrument feature comes in. In order to see these early galaxies and stars, we have to look deep in space and look back in time. This is because light takes time to travel from there to here. So the deeper we look in the space, the back in time we look. But we know that the universe is expanding. So these distant objects are moving fastly away from us. Because of the Doppler redshift, the visible or ultraviolet light they emitted when they were born will be infrared when they come up to us. James Webb Telescope is optimized to detect this infrared light. Webb will address several key questions in this theme. What are the first galaxies? When and how did reionization occur? What sources caused reionization? Using infrared spectroscopy, it will find and identify the first galaxies to form in the early universe. In addition to the first light from the first galaxies, the James Webb Telescope can also observe how these galaxies are assembled. Because of the previous telescopes, we know the sequence of galaxy assembly. This sequence is called Hubble sequence. In this sequence, the dark matter, gas, stars, metals, and other structures start to merge. Interestingly, this galaxy assembly process is still occurring today. For example, the Andromeda Nebula is heading toward the Milky Way for a possible future collision. It seems like we know a lot about these galaxies, but there are still several questions Webb is hoped to answer. We don't really know how these galaxies are formed, what controls their shape's formation, and what makes them form stars. We don't know how the chemical elements are generated and redistributed through the galaxies. We also don't know the influence of central black holes over the galaxies. Webb's telescope will address several key questions in this theme. When did the Hubble sequence form and how did it form? How did the heavy elements form? What physical processes determine galaxy properties? What are the roles of black holes in galaxy evolution? We have been observing stars for thousands of years. It has been a main topic of astronomy for so long. But it is only in recent times we have started to finally understand them, thanks to the detailed observations and computer simulations. 100 years ago, we didn't know that stars are powered by nuclear fusion. And 50 years ago, we didn't even know that stars are continually being formed. There are still so many open questions about the birth of stars, such as why stars form in groups, and how planetary systems like ours are formed. Young stars within a star-forming region interact with each other in complicated ways. The questions about the evolution of these stars, how they throw away metals back into space for the generation of new stars and planets, are still unanswered. In order to better understand how planets are formed, we need substantially more observational input. James Webb Space Telescope will address several key questions in this theme. How do protostellar clouds collapse? How does the environment affect star formation and vice versa? What is the initial mass function of stars at substellar masses? How do protoplanetary systems form? How do gas and dust coalesce to form planetary systems? Webb will be able to observe stars at all phases of their evolution, from protostars through the formation of planetary systems. It will be able to penetrate the dust to determine the physical processes that produce stars, planets, and debris disks. In order to solve the massive star formation paradox, Webb with its mid-infrared detection will provide deep high spatial resolution imaging from the dense very young cluster cores. One of the main objectives of astronomy is to be able to understand the origin of the Earth, and why is it able to support life. The key part of the story is to understand how planetesimals are formed, and how they can combine to form larger objects. We still don't know how planets reach their orbits, and what are the effects of large planets on smaller ones like our own. Another key objective is to determine the chemical and physical history of planetary systems like ours, and to investigate the potential for the existence of life in those systems. To trace the origins of the Earth and life in the universe, we need to study planet formation and evolution. The search for life in our solar system and other planetary systems is extremely fundamental to understanding what our place is in the cosmos. Webb will be able to provide crucial data for understanding the origin of planetary systems, and the potential for other habitable regions. So there are several important questions James Webb Space Telescope will be able to answer in this theme. How do planets and circumstellar disks like our solar system formed? How are habitable zones developed and what is their nature? Using the massive amount of data, it will be able to determine the physical and chemical properties of planetary systems including our own, and investigate the potential for the origin of life in those systems. Webb will investigate exosolar planets and debris disks, and will compare these observations to objects within our own solar system to detect life on those planets. Not only that, Webb is also designed to be able to observe objects in our solar system. Webb has near and mid-infrared sensitivity, so it will be able to observe and study virtually all known Kuiper belt objects. But because of the very large infrared brightness of Mars, Jupiter and Saturn, it might limit Webb's observations of these planets. Dark matter is the unseen matter which is responsible for a large fraction of the mass of galaxies. Unfortunately, Webb will not be able to directly detect this dark matter. This is because Webb is not designed to be a dark matter detection instrument. We have other instruments for this purpose. However, Webb will be able to indirectly measure its effects. One way is via the gravitational lensing effect. In Einstein's general relativity theory, a light beam passing near a large mass will be slightly deflected. Using the gravitational lensing phenomenon, when astronomers have pictures of distant galaxies, they can calculate how much of the total mass is missing. The missing mass is then presumed to be dark matter. Webb is optimized for this type of measurement, because it will provide very sharp images. This will allow very small disturbances to be measured. Webb can go so deep in space, which gives access to many more background galaxies for measuring gravitational lensing disturbances. With so much data it can provide, scientists can compare these observations to theories of the role that dark matter played in that process. This will lead to some understanding of the amount and nature of dark matter in galaxies. So while Webb will not be able to directly detect dark matter, it will provide so many insights that are very useful. Now that we have discussed the role of Webb on dark matter detection, let's talk about another interesting phenomenon, which is dark energy. About 70% of the universe consists of mysterious dark energy, which is pushing on the expansion of the universe and causing it to accelerate. Again, Webb is not designed for dark energy detection. NASA is planning future telescopes for research of dark energy, which includes massive observation of supernovae. In contrast, Webb will make fewer observations of supernovae. However, by observing them at higher redshift, fainter levels, and further into the infrared, it will provide complementary information to this future research. So these are the 5 observations I am excited about Webb's telescope. Let me know in comment which one you found exciting. And please subscribe and like for more of these kinds of videos in future.